Okay, so in this lecture, I'm again analyzing the Galilean projectile. If you remember what the Galilean projectile is, this motion of this ball you see on the video. We have a ball on the table and it's just going on a straight line path with some constant velocity, and it comes to the edge, and from the right that put this point on, it goes off the edge, and it is, from this point on does this horizontal projectile motion up in the air, and it falls down. So in order to model, first what we do is just we take the raw uh, data, and raw data means that what is the position of the ball at every frame. For that, we just produce, by using the track new point mass, we produce mass A, okay? And I already did this. What the tracker does is just, it is just taking the position of all position of the ball at every, you know, at every. Let me enlarge the fonts a little bit. Position of the ball at every frame. So you see at every frame, if you just enlarge it, this how the tracker takes the position. So just we take the midpoint of the ball as reference. So more or less you can take these points as the actual position for the object. And next is we are going to, let me change this trail to long trails, okay, and just disappear the paths. Okay, so these are the the position at every frame. So now next what we do is we're going to make a model, but we're going to produce two models. And the other thing is that, first let me also say that this is the coordinate axis that I put. As you see, the coordinate axis, I take not the initial frame, the location of the ball at the initial frame, but rather write the point that the ball goes off the table. So I took this origin of my coordinate system as the point that the ball goes off the table, right at the edge. Okay, this is the point. It's frame number 17 is the frame that the ball is supposedly leaves the table. Okay, so also of course this there is a meter stick. For the meter stick, we just produce this calibration saying that this distance is going to be 1 meter, obviously. So we have done these before. So the first model that I already created, but I'm just this is invisible to you. Let's run this video. Okay, the first model I created, I will call that as model A. The model A, now I will make it visible. So the model A is these blue circles. All right, that gets back to the origin. So this is the blue circle is just, as you see, following the uh, location of the ball at every frame. And how did I create this is that, this is the model building window for, let's enlarge this a little bit more. What you see is model builder window. Okay. And model builder window, obviously these first sets are the parameters. Well, I take, for example, for the first parameter as the G's gravity G, which is 9.81 set to, and x0 is just the location of the ball with respect to the coordinate system I put, which is right the edge of the table, the position of the ball when it leaves off the table, when it goes off the table, and this is another parameter. And these are the initial values. So the model is I'm producing is dynamical model, and for dynamical models, what we do is we are just putting a force function. Obviously, there is no any force in the horizontal direction that we put f is equal to 0, but on the horizontal in the vertical direction, we have this gravity, but this gravity is acting only after the ball goes off the table. So we cannot simply put over here, we cannot simply put the force is equal to minus m times g, because before it goes off the air, it goes on the table. While on the table, there is no net force acting on the ball. So the force is two parts. Let me write it over here. Let me create. Okay, let's close this first. A new tab. So the force in the y direction is minus mg when the ball up in the air, but it is 0 when it's on the table. It is 0 when it's on the table because its mass is just this is the ball goes on the table in this direction. There is still mass pulling it down, but there is also the normal force acting on the ball by the surface of the table, which is normal n. And if it goes in the horizontal direction, n is equal to mg, so there is no force in the y direction. So until the ball comes to edge, the force is 0. Right from the edge, the force is minus mg. And the thing is, how do you model this in the model building window? Obviously, the force function is conditional. We can put we put this conditional expression in tracker with this command line. If we type just if and open a parenthesis, okay, put your condition. Well, for example, we just from the first model, we take the condition as the position of the ball x. When x is larger than x0, x0 is the position of the ball right at the edge. Take the force as minus mg, because this is x is equal to x0. If the position of the ball is larger than x0, that means it's going to be right to this point. If it's right to this point, obviously the ball is up in the air, and while up in the air, the force must be mg. And we put a comma. If this condition is not met, that means if x is less than x0, the ball is on to the left of the point, and while the ball is over here, obviously the force is 0, so put 0. This is how we type the model, the force function in the model builder window on the tracker. So this is the condition. If the condition is met, use this. If this does not met, if this is not satisfied, use this. So this is the way we model the force conditional forces. So if I get back to again, so you see over here, this is how we type. This is the condition x is larger than x0, then take force as minus mg. But if not, then take this as 0. Okay, so this is the way we model, and I'm just erasing this so that you can see it well. So the rest is determining the initial values. Of course, the initial values, we always start the time at 0, and initial position of the ball in the first frame. Well, since we already set our coordinate system to the corner, to the edge of the table, obviously initial position of the ball is going to be on the negative x-axis, and this is, I put minus 0.852 centimeter, so in terms of meters, of course. This is the initial position, and of course y is 0. There is no any initial position in the y, it's on the x-axis. And Vx is the initial velocity, and we just put 1.5 meter per second because this makes the model that follows at every frame the ball. Okay, if for example I put like 1.4, you see what happens. You see, that's these blue circles that lives behind the ball. Well, by just trying and tribulations. So if I just put a larger value like 1.6, it goes ahead. So by trial and error, and I just found this should be 1.5. Okay, and obviously it will go at a straight constant velocity right until it comes over here, and from this point on, now the tracker lets the computer knows that okay, now you have to take a non-zero force from this point on, and the force is going to be minus mg. Well, putting mass any value, it doesn't make any difference, because up in the air, all objects regarding the mass will do the same type of path, will follow the same type of path, as long as what the initial values in the velocity is. So it doesn't matter whether you have a 1 ton of mass or 1 gram of mass, it's going to be just the same. So from that point on, the tracker is just calculating the motion in such a way that it is acted by gravity now. So it goes to the bottom. Well, as you see, this model is very successful with these values, but you can still measure its success by doing this. We have a tool. We have a tool which is measuring tools. Among the measuring tools, tape measure. I'm just producing this tape measure, and the tape measure is just can measure. It's a kind of you see what you see over here. It's a kind of arrow point. It has both ends, and it measures the distance between these ends. But I can always do this, just to fix one end to the raw data, yes, and the other end is to the model A, the model that I produced. So that means that one end of the tape measure is going to be fixed to the actual position of the ball, and the other end is going to be the position of the model that we have just produced. So since supposedly that model should follow the position of the actual ball, obviously you should expect a very small difference. And let's look at the tape measures value over here. This is tape measure, and tape measure is having this length measurements. Okay, let's stop this. You see, tape measure, I mean, what you see over here for every point at this frame, whatever the frame corresponds to this, at this frame, what is the difference, position difference between the actual position of the ball and the model position that we produced? And this tells you that, okay, when you look at this, just between 2.5 millimeters and 3 millimeters at this point. And at every point, the tracker, the tape measure is just measuring the difference between two locations. Well, of course, you will expect that this measurement should be closer to zero if you have a very successful model. But what you see is, in fact, all the measurements are on the order of millimeters. It runs from like 1 millimeter until it's 6.5 millimeters. So at most, the most discrepancy is appearing is somewhere like to the end of the video over here. It measures like a 6.5 millimeter difference, but it's millimeters, It's millimeters is not much different. And you can see this. Let's look at this frame. Okay, let's look at this frame. So let's check whether there is a difference. Yes, in fact, there is this difference. And when I enlarge, this is the actual position of the ball, and this is the model position that we produced. Well, there is some difference, but still, this is still very close to the center of the ball. It is at least on the ball, right? The model still follows the ball. but you know, there is some discrepancy. Well, you can just try to change the parameters over here in order to match this model position to the actual position of the ball. But if you make this matching almost perfect for the last frame, you will see that other frames will be having different different differences. Maybe you enlarge, and this is what I get by playing with these parameters. For example, in this frame or in this frame, in the frame over here, this frame has the least discrepancy. This is the frame number, let's say, let's check, is 24 frame. They almost match up. They almost match up, but other frames has some differences. So I mean, you can just play with this. You can play with the parameters so that on average, you can always take the average of all these measurements. You can always play with these parameters so that on average you have the list of these measurements, tape measurements. Statistically, average of these measurements becoming list means that you have the most successful model. Okay, so this was one way of modeling by using this if conditional. And the other model that I produced, well, this if conditional is that just implements the force function according to the position of the ball. Okay, the position of the ball when it's very close to the the origin. Well, this x-ray is very small number, 0. Almost origin, but I made this very small adjustment so that my model becomes successful. So almost is at the 0. So when the x is less than 0, take the model that f is equal to 0 when the x is larger than 0. So I mean, this condition that is looking at the position. You can do this model, this condition on not the position based, but the time based. I mean, if the time is whatever the timing of this frame, this 20, well, what is the frame? This frame is, let me come over here. This frame is the 17th frame. And whatever the time of this 17th frame is, until that time, whatever this corresponds to how many seconds, until that time, I can also, put this condition until that time, just take the force as 0, and from that time on, afterwards, take the model as f is equal to minus mg. So now, let's see how this model is modeled in if conditional. So let me just switch to model B. Now, model B models are force function based on time measuring, and it is based on a time condition. You see over here inside the if conditional, we have the conditional is t about the time. When the time is larger than t0, what is t0? T0 is the frame, the time corresponding to frame number 17. And the frame number 17 is the frame that the ball is leaving the table. It goes off the table. Okay. So this time is found to be 0.564 seconds. So until after that time, you just take the force as minus mg. But if this condition does not matter, if the time is less than this value, 0.564 seconds, take the force to be 0. You can also model your, model with this conditional based on time. Remember, the previous model was based on the position. You see now we modeled the force as the condition based on the position measurement, or you can model by using time. Okay. All right. Also, you can also for model B make the model B visible. Okay. Let's make model A invisible, so model B visible. Okay, so you see model B is the model which is shown by these orange colored circles. Orange colored circles as model B. Well, it's using almost the same parameters, the same 9.81, the same initial position, the same velocity before it goes off the table, 1.5. It follows very nicely the location of the actual position of the ball, and after it goes off, it implements the force based on the time. So it is again, you see it's following very nicely the location of the ball at every frame almost. Well, the last frame over here, you see there is still some discrepancy, as you see. When you enlarge it, this is the actual position, when this is the model position. Of course, you will still have some difference, and it's order of 5.6 millimeter. But the model is successful, so at least you can say that every frame it follows the location of the ball. You can still just measure the success of your model B by creating another tape measure tool and attaching this tape measure tool one end to the actual position of the ball and the other end to the model position. So you look at the tape values. Let's create a new tape. Let's do this. Okay. So come over here, new measuring tool, tape measure, and now this is the new tape measure, but attach ends, one end to mass A, which is actual position of, and the other end model B. So let's look at how does it go. And you see again for model B, these numbers are on the order of millimeters. It looks better. I mean, it's like this was 6.5 millimeters for the previous model. This looks like 6 millimeter, order of 6 millimeters, but almost the same, almost in the order of millimeters. And the most successful point is like 0.5 millimeter right at this point. The worst point is this point, which is 0.6.3 millimeters. But anyway, I mean, this is another successful model because all the points are all the measurements are like on the order of millimeters. As I said, these are the tape measure values. I mean, this is the difference of the actual position of the ball with the model that you produce. I mean, it goes like 2 millimeters to 3 millimeters. So millimeters is not big difference because the ball is like almost maybe 5 centimeters diameter. So okay, that's it. This is how you model if we have condition that the force is changing. This is a dynamical model. If the force, if your object is experiencing different forces, and this is how you model. With different forces. You put conditions, and the tracker implements according to this condition which force value should it implement on every frame. So this is the way it does.